And as a disclaimer, the only difficult part about this section is if you're not really good at multiplying out polynomials and collecting like terms and then factoring. And that's why your prerequisite skills was focused so heavily on those kind of things, because you needed to remember how to do that. So now we will talk about tangent lines to start with, because you remember last section we were interested in finding slopes of tangent lines. Okay? And remember, the definition of tangent line is that it touches the curve in exactly one point, but I didn't make one additional requirement, which would lead us into a bad problem if I don't. So a tangent line it touches the curve, but it doesn't cut the curve. It doesn't, what is called mathematically, it does not bisect the curve. It doesn't divide it into two equal pieces. So the reason I'm making that distinction is because the line through P1 is in fact a tangent line. P2 is not a tangent line. Because it actually bisects the curve. It cuts it in half. Okay? P3 is a tangent line. The point P3, that line is a tangent line. P5 kind of obviously isn't then. So the only one we have a question about is the line at P4. Okay? P4 appears to violate that definition, because it does start below the curve over here and come out on the other side above the curve. So it appears to be cutting through the curve. Now here's the part that you're going to have to imagine with me on. That happens because that line is so long. If I was able to have that line be just that one single point, which I know is not a line, it's a point, then it could be a point of tangency. It's just that I can't put the line over that point without cutting through it, because anything that adds the other point is going to make it come out on the other side and cut through it. So P4 is a kind of an unusual kind of exception to some of our rules. And we're going to talk about later on why P4 is going to be a place where we can say, yes, we can take a derivative, therefore there is a slope of a tangent line there. But on the others, you can't. So right now, there's going to be some things a little bit fuzzy for you. So for now, we're not going to worry too much about trying to find derivatives at points like P4. What's special about P4 is it's called an inflection point. Okay? An inflection point is where a curve starts changing concavity. So in other words, this curve is concave down right along there. And it continues to be concave down, but somewhere between here and here, it turns back concave up. And the point where, just for an instant, it's neither concave down nor concave up, let's call that P2.5, that point is a point of inflection. It's decreasing sharply, but then it actually is leveling out. And then what happens here is it's going from being concave up. At this point, it's actually changing and going to being concave down. So P4 is kind of a special point. And it's called an inflection point. What we looked at in the last lesson was we talked about secant lines. This is a secant line. Well, I used to be a secant line, so I messed it up. That secant line has a slope. And the slope of that secant line is f of a plus h minus f of a over h. If we can make h small enough, we can make that secant line approach a tangent line. So if we're trying to find a line that's tangent to the curve at R, and we're going to try to find its slope, then what we would do is we would start out by thinking about, well, okay, here's R. Here's another point S that's, well, it's kind of pretty far away from R. And we could take that secant line and find its average rate of change, or its slope, but it doesn't tell us much about what's going on with the curve, because it doesn't tell us much about what's going on right here. But if we were to slide that point a little bit closer and go through S2, well, that means it would get a little bit closer to being an actual tangent line, but it's still a secant line because it's 2 points. So at this point, we would still get an average rate of change. But the average rate of change here, the slope here, would be closer to being the slope at R than what this line's slope is. And if we could slide it closer still down to S3, the average rate of change, again, because it's a secant line, is a little bit closer to being the slope of the tangent line. If we continue that process and we get the average rate of change here, that average rate of change is a lot closer to being the actual slope of the tangent line than the slope of this line was. So what we're doing when we take the limit of a function and we take f of x plus h minus f of x over h, and we're trying to let h get really, really tiny, what we're doing is we're sliding the point closer and closer and closer until it's as close to on top of the point of tangency as we can get, which is why we're trying to let h approach 0. We're trying to get 2 points that are some distance h apart, but we're trying to shrink that distance down so much that you can't tell the difference between those 2 points. They look just alike. And when we do that, then we can take the slope of that tangent line, and that'll give us the slope of the curve at that point. The slope of the tangent line approximates or is the same as the slope of the curve. They have approximately the same slope. And the slope of the curve at that number R is the rate of change of that curve. So that's the instantaneous rate of change. Where all of these were average rates of change. Okay? That's the whole idea behind what a derivative is. Now, taking a derivative will be much easier in Chapter 12, because the only way we're going to learn to take a derivative in this chapter is the algebraic method. It's called the four-step process. And we actually practiced a little bit in the last section. So the first example we've got here says, consider the graph of f of x equals x squared plus 2. And I've actually drawn us a picture of x squared plus 2, so we can draw on it. So this is the curve, x squared plus 2. So that's f of x. Okay? Our first job that we're given is to find the slope in the equation of the secant line. Secant line tells us we're going to have 2 points through the points where x is equal to -1 and x is equal to 2. So the first thing we're going to do is we're going to, on the picture, we're going to find the slope of the line that connects up the point -1, 3, and the point 2, I believe that's 6. Yep, that's 6. It's not 5. This was nicer on my other, if I printed it out in colors, because this is black and white and it's hard to read. So what we want to know is what is the slope of that line, and then once we get the slope of that line, what's the equation of that line? And that's something we did in 1630. So given that we have the actual function here, f of -1, we already determined, same thing as -1 squared plus 2, which is 3. So that's the point -1, 3. And f of 2 is 2 squared plus 2, which is 6, which gives us the point 2, 6. And to find the slope, which is your average rate of change, but it's the slope of the secant line, we take the point 2, 6, x's go on the bottom, y's go on the top, and the point -1, 3, and we do the slope formula on it. And the slope formula, basically, you remember, it's the difference in the y's over the difference in the x's, and you divide one into the other. So 6 minus 3 is 3, and 2 minus -1 is 2 plus 1, which is 3, and 3, excuse me? Yeah, it just equals 1. So the slope of our secant line is 1. And because it's a secant line, it has a formula that follows along with y equals mx plus b. That's the form of a line. Slope, y-intercept. And because I have 2 points to pick from, you can pick whichever point you want. I'm just going to arbitrarily pick the first one. And this first point, -1, 3, gives me an x value, which is -1, and an f of x or a y value, which is 3. So if y is 3, and the slope is 1, and x is -1, the only thing I don't know is b. And it's not hard to find b because it's just arithmetic. 1 times -1 is -1. So I'll add 1 to both sides. 3 plus 1 is 4. -1 plus 1 drops out. And that tells me then that b is equal to 4. Because I've got 4 on one side and b on the other. So that tells me then that my equation is y equals 1x plus 4, or simply y equals x plus 4. That's the equation of the secant line. Okay? Now we're going to try to do something similar, but now we want to find the slope of the tangent line. We're going to find the slope and the equation of the tangent line. In order to find the slope of the tangent line, this is a slope formula. Remember that h is simply a plus h minus a, and the a's actually drop out and give you that h. So that really is, we're taking the limit as h approaches 0 of a slope formula. And we have a formula for that, so we're going to start at -1. F of -1 is equal to -1 squared plus 2, just like it was before. So f of -1 is still 3. And all we're going to do is replace a in both of these with -1. So f of -1 is 3. We've taken care of that part. H is still on the bottom, and out here at the end we've got -3. Now we need to find f of -1 plus h. So f of 1 plus h is -1 plus h squared. -1 times -1 is +1. Minus 1h, and when you multiply the other way, it's also minus another h, so that's going to be minus 2h plus h squared plus 2. And 1 plus 2 is -2h plus h squared plus 3. So f of -1 plus h is -2h plus h squared plus 3. And you always want to see this happen when you do this. If this doesn't happen, then you know you've messed up the arithmetic somewhere. You probably miscopied a number. Because what should happen now is that any constants, any non-h terms, should cancel each other out. And they do. This 3 is canceled out by the value of f of -1. So what we have now is -2h plus h squared over h. So we'll factor out the h. So we can get rid of it. And now we'll take the limit as h approaches 0 and dwindles away into nothingness of the quantity -2 plus h. And if h approaches 0, it disappears eventually, and all we have left is -2. So the slope of the tangent line is -2. And we still have that one point. X is -1, y is equal to 3. So we're going to do the same exact thing we did a minute ago. We're going to say y is 3 minus the slope is -2. So 3 is equal to -2 times the value of x, which is -1, plus b. And -2 times -1 is +2 plus b. So 3 is equal to +2 plus b. And in order to move the 2 to the other side, I have 3 minus 2. So that tells me that B is equal to 3 minus 2, or B is equal to 1. So the equation of the tangent line is y equals negative 2 times x plus b, which is 1. And there's your equation. Can you handle that? Slowly? Yeah, and our brains are tired at this point, too. I understand. Okay. Okay, you got what you need? Okay. Remember, our tangent line is y equals negative 2x plus 1. That means the y-intercept is 1. 0, 1. Our slope is negative 2, so I'm going to go down 1, 2, and write 1. Then I'm going to go down 2 and write 1. So if we did what we were supposed to do correctly, we should be finding that that line touches that curve at negative 1 and nowhere else. So there's your tangent line. And here's your point of tangency. The only point the curve and the straight line have in common. Okay? Now, I wouldn't expect you to graph this by hand. But I will. I showed you this for a reason. You've gotten the slope of your tangent line, and you've got your equation of your tangent line. Get your calculator in, and y1, put your function that you were working with. And then underneath that in y2, put the equation of your tangent line, and hit graph. You should see the tangent line touch the curve. If it cuts through the curve, something didn't go right. But the graph should verify that you did all the math right. Okay? So this is a picture of what I just showed you. Now I'm going to graduate to actually taking something called a derivative. And I'm going to begin this by telling you that finding a derivative, what a derivative is it's a formula for the slope or rate of change of a function at any x value in the function's domain. And for you to understand why that would be a valuable thing to be able to do, they could have asked us to find the equation and the slope of a tangent line at x equals 3. on that last problem. And then to do it at x equals 5, and then at x equals -7. And you'd have to go through all the arithmetic over and over and over and over again. That would get easy. So what we're going to do is we're going to do something called the four-step method to find the derivative. It's also referred to as the definition of the derivative. This is how you find the derivative. The first thing you do, this is the steps. Your first step is to find f of x plus h. Your second step is to find f of x plus h, which you already found, minus f of x. Your third step is to find, and when I say find, I find and simplify f of x plus h minus f of x